All right, everybody, welcome back. Ready for another deep dive?
Absolutely. Always ready to explore some cool science.
Today, we're going to be looking at a topic that's absolutely electrifying.
Ooh, I think I know where you're going with this.
We're talking electricity and magnetism.
Two of my favorite things. They really go hand in hand, don't they?
They really do. And we're going to be looking at them specifically through the lens of the North Carolina Standard Course of Study for 6th grade science.
That's a great place to start. It's all about laying a strong foundation, right?
Exactly. But don't worry, this isn't just for 6th graders. We're going to go beyond the basics and uncover some pretty amazing real-world applications.
Yeah, these concepts are way more relevant to our everyday lives than most people realize.
Absolutely. So first things first, let's talk about the difference between static and current electricity.
All right, so let's start with something everyone's experienced. Static electricity.
Yeah, like when you walk across a carpeted floor and then touch a doorknob zap.
Exactly. That sudden jolt, that static electricity in action.
So what's actually happening there? What's causing that zap?
It's all about electrons, those tiny particles that carry electric charge. When you shuffle your feet on the carpet, you're picking up extra electrons.
Uh-huh, so you're getting all charged up.
Exactly. And then when you touch something metal, like a doorknob, those extra electrons have a path to escape, and they do it quickly.
Hence the zap.
Precisely. So that's static electricity, a sudden discharge of built-up charge. But then we have current electricity.
Which is what powers our homes and all our devices, right?
You got it. Current electricity is all about the continuous flow of electrons through a conductor.
A conductor. So it's like the electrons are flowing through a pipe.
That's a great analogy. Think of a copper wire as the pipe, and the electrons are the water flowing through it.
And what makes something a good conductor? Like why copper and not, say, rubber?
It all comes down to the atom structure and how easily electrons can move within it.
So in copper, the electrons are freer to roam around.
Exactly. In good conductors, the outermost electrons are loosely bound to the atoms, so they can easily jump from one atom to another.
So they're kind of like nomads, wandering from atom to atom.
That's a fun way to think about it. Now, in materials like rubber, the electrons are much more tightly bound. They're stuck in place, so they can't flow easily.
So rubber acts as an insulator, blocking the flow of electricity.
Precisely. Insulators are just as important as conductors when it comes to electrical safety and making sure electricity flows where we want it to.
It's like they're directing traffic.
Yeah,
Okay, so we've got this flow of electrons, but how do we actually control it? That's where circuits come in, right?
absolutely. A circuit is a closed loop or pathway that allows electricity to flow.
And this is where Ohm's law comes into play. I remember learning about voltage, current, and resistance, but it always seemed a bit abstract.
I hear you. It can be a bit tricky to wrap your head around. But think of Ohm's law as the rule book for how electricity behaves in a circuit. It tells us how these three things are related.
Okay, break it down for me.
So voltage is like the pressure that pushes the electrons through the circuit.
Got it, like the force behind the flow.
Right. Current is the actual flow of electrons, how many are passing a point per second.
Okay, so that's the rate of flow. And then what about resistance?
Resistance is anything that opposes the flow of current.
So it's like the friction in our water pipe analogy.
Exactly. The narrower the pipe, the more resistance there is to the flow of water. Similarly, the more resistance in a circuit, the harder it is for current to flow.
Okay, I think I'm starting to get the picture here. So if you increase the voltage, you'll get more current flowing.
As long as the resistance stays the same, you got it. And if you increase the resistance, the current will decrease.
So it's all about balance. This is why we need different size wires and fuses and things, right?
Right, we have to make sure the components in a circuit are designed to handle the specific voltage and current they'll be exposed to.
Otherwise, things could get overloaded and overheat, like with a short circuit.
Exactly. Safety first. Now, speaking of circuits, did you know that there are different types?
Yeah, I remember learning about series circuits and parallel circuits. But to be honest, I can't quite recall the difference.
No worries, it's a common point of confusion.
Mhm.
Think of it this way. In a series circuit, all the components are connected in a single loop, one after another.
So the current has only one path to follow.
Exactly. And that means if one component fails, like a light bulb burns out, the whole circuit breaks and nothing works.
Ah, like those old school Christmas lights.
Yeah,
One bulb goes out, the whole string is dark.
you got it. Now, in a parallel circuit, each component has its own separate branch or pathway.
So the current has multiple routes it can take.
Exactly. And this means that if one component fails, The other components on the other branches will continue to work just fine.
So that's why modern Christmas lights stay lit even if one bulb burns out.
Right. Parallel circuits are much more reliable, and that's why they're used in most electrical systems today.
Makes sense. Okay, so we've talked about the flow of electrons, circuits, and Ohm's law. But what actually makes electricity flow easier or harder through a wire? I mean, besides the type of material, of course.
That's a great question. There are actually several factors that can affect the resistance of a wire.
Like what? Spill the secrets.
Well, first off, the thickness of the wire plays a role. Think of it like this. If you're trying to drink a milkshake through a straw, it's going to flow a lot easier through a wider straw, right?
Right, definitely.
It's the same with electricity. The thicker the wire, the less resistance the electrons encounter as they flow through it.
So a thicker wire is like a wider highway for electrons.
Exactly. And on the other hand, a thin wire is like a narrow, winding road, much more resistance.
So thicker wires are generally better for conducting electricity. What else affects resistance?
The length of the wire also matters.
Oh, that makes sense. The longer the wire, the further the electrons have to travel.
Right. And the more they have to travel, the more opportunities they have to bump into atoms in the wire, which slows them down.
So it's kind of like a long road trip. The longer the trip, the more chances for traffic jams.
I like that analogy. So shorter wires generally have less resistance than longer wires.
Got it. Anything else?
You bet. The temperature of the wire can also affect resistance.
Really? How so?
Well, as the temperature of a wire increases, the atoms within the wire start to vibrate more vigorously.
So they're kind of jiggling around more.
Exactly. And all this jiggling makes it harder for the electrons to flow smoothly through the wire. They end up bumping into the atoms more often.
Ah, so it's like trying to navigate a crowded dance floor. The more people dancing, the harder it is to move around.
Perfect analogy. So as the temperature goes up, the resistance generally goes up as well.
Okay, so thicker, shorter, and cooler wires are the best conductors.
You got it.
Fascinating. Now let's shift gears a bit and talk about something seemingly unrelated. Magnets. I remember playing with them as a kid, but honestly, I'd never really understood how they worked.
They do seem kind of magical, don't they?
Yeah, like how do they attract or repel each other without even touching?
It's all about magnetic fields. You see, inside magnetic materials, you have these tiny regions called magnetic domains.
Magnetic domains.
Yeah, they're like mini magnets themselves. And in a normal piece of iron, these domains are all jumbled up, pointing in random directions.
So they're kind of disorganized.
Exactly. But in a magnet, these domains are all lined up in the same direction. And this alignment creates a magnetic field, an invisible force that extends out from the magnet.
So it's like the magnetic domains are all working together to create this powerful field.
Precisely. And this magnetic field is what allows magnets to interact with each other and with certain metals.
I always loved how you can't see the magnetic field itself, but you can see its effects. Like when you sprinkle iron filings around a magnet.
Yeah, that's a classic demonstration. The iron filings align themselves along the magnetic field lines, making the invisible field visible. Pretty cool, right?
Totally. Now, here's a mind-blowing question.
Yeah.
What do magnets and electricity have in common?
Great question. They're actually two sides of the same coin.
Wait, what? You're telling me magnets and electricity are connected?
Absolutely. They're intimately related. In fact, you can create a magnet using electricity.
Whoa, really? How does that work?
It's all about the relationship between electricity and magnetism. When an electric current flows through a wire, it creates a magnetic field around the wire.
So electricity can create magnetism.
Exactly. And if you coil the wire, you can concentrate the magnetic field, making it even stronger.
And that's how you make an electromagnet.
You got it. An electromagnet is simply a coil of wire with an electric current flowing through it. And the cool thing about electromagnets is that you can turn the magnetism on and off by controlling the flow of electricity.
So it's like a magnet on demand. Why is that so useful?
Well, for one thing, it allows us to create really strong magnets that we can control precisely. We can make them as strong or as weak as we need, and we can turn them on and off whenever we want.
That's amazing. Where do we see electromagnets in action in the real world?
They're everywhere. They're used in electric motors, which are found in everything from cars to power tools. They're used in loudspeakers to create sound waves. And those giant cranes you see at scrapyards that lift cars, yep, those use electromagnets too.
Wow. I had no idea electromagnets were so versatile.
They really are essential for so many modern technologies.
So just to recap, we've learned about the difference between static and current electricity, how circuits work, the factors that affect resistance, the invisible world of magnetism, and the amazing power of electromagnets.
And it's all connected. Electricity can create magnetism, and magnetism can create electricity. It's a beautiful dance of fundamental forces.
It really is, and the story doesn't end here. We've just scratched the surface.
Exactly. Think about all the incredible technologies that rely on electricity and magnetism. How will they evolve in the future?
Yeah, what new possibilities are on the horizon? I mean, could we one day have wireless power transfer or levitating trains based on these principles?
Those are great questions. And those are the kinds of things scientists and engineers are working on right now. Who knows what amazing innovations the future holds?
So to all you budding scientists out there, keep exploring, keep asking questions, and who knows, maybe you'll be the one to make those futuristic technologies a reality.
The world needs more curious minds like yours, so don't be afraid to dive deep into the fascinating world of science.
Hey, don't keep all this amazing knowledge to yourself. Share it with your friends, family, and classmates. Maybe you can even spark some lively discussions in your science class. Keep those brains buzzing, everyone.
Until next time.
See you later.